Welcome to Manimated AI. Every matrix tells a story about how space moves, stretches, rotates, and how we can understand the world through transformation. All right, welcome back. In this video, we're going to pull together everything you've learned from our previous lessons and see how it all comes alive on a grid. By the end, you won't just understand the math, you'll see it happening right in front of you. Let's begin with a simple idea: transformation. So, what is a transformation? At its core, it's a type of function, something that takes in an input and gives back an output. But in linear algebra, we think in vectors, and transformations take in a vector and gives out a new vector. For example, this vector here might land over there after a transformation. You can think of it as the vector being picked up and moved somewhere else. So why use the word transformation instead of just calling it a function? Because transformation captures something deeper, it hints at a visual movement in space. It's not just input-output, it's space itself being reshaped. Because while a regular function maps numbers to numbers, a transformation maps vectors to vectors. But transformations aren't just about what happens to one vector. So how should we think about transformations, not just for one vector, but for all vectors? Here's a powerful idea. Instead of focusing on the arrows, let's just look at where their tips land. Each tip is a point. That way, imagining a transformation becomes imagining every point in space moving to another point. And for transformations in 2 dimensions, a great trick is to visualize how an infinite grid of points moves. Watching this happen gives a beautiful feeling. It's like stretching, twisting, transforming space itself. Mathematically, we write it like this: for every point, there's a new point. This visualization helps us understand how transformations affect all of space, not just individual vectors. So, transformations affect every point in space, but not all transformations behave the same. Next, let's explore what specifically makes a transformation linear. Okay, so we know a transformation moves vectors around, but what makes one of these transformations linear? In linear algebra, not every transformation qualifies. There are 2 specific rules a transformation must follow to be called linear. Rule 1. A linear transformation never bends space. Every straight line in the input must remain perfectly straight in the output. Imagine you draw a line, like one stretching across your screen from left to right. A linear transformation can stretch it, rotate it, or tilt it. But it can never turn that line into a curve. If any line gets warped, even slightly, that transformation isn't linear. Let's take a closer look at what happens when we look at all the points in space. In this transformation, lines become curves, a clear violation of linearity. Here's another violation: when the origin moves. Even though lines stay straight, moving the origin breaks linearity. Sometimes the violation is subtle. Here, horizontal and vertical lines stay straight, but watch what happens to this diagonal line: it curves. Finally, here's a true linear transformation. Lines stay straight, and the origin stays fixed. This is what a linear transformation looks like. These visual rules correspond to important algebraic properties that define linear transformations. So, why do these rules matter? Because they give linear transformations a kind of structure, one that we can understand, work with, and even reverse. They preserve relationships, they keep the math elegant, and most importantly, they form the foundation for almost everything else we'll study in linear algebra. If you can recognize a transformation as linear, you can analyze it, model it, and build on top of it. Now that we know what a linear transformation is, here's the next big question. How can we describe a linear transformation numerically? After all, if you wanted a computer to animate this, you couldn't just say squish space, you need numbers. Amazingly, it's enough to know just 2 things. Where the basis vector I hat, pointing along the x-axis lands, where the basis vector j hat, pointing along the y-axis lands. That's it. Track those 2, and you know everything about the transformation. Every other point's motion depends entirely on where these 2 basis vectors go. These two vectors completely determine how the transformation affects every point in space. Now that we know where I hat and j hat land after the transformation, here's the beautiful part. We can figure out where any other vector goes. Any vector is a combination of I hat and j hat. For instance, let v be -1 I hat plus 2 j hat. After the transformation, v goes to -1 times where I hat lands, plus 2 times where j hat lands. Same linear combination, but now using the transformed basis vectors. This preserves the structure of space, linear combinations before and after match. Now, here's the really exciting part. All the information we've been using, the new positions of I hat and j hat, can be neatly packaged into a simple object called a matrix. Specifically, we organize the transformed basis vectors into the columns of a 2x2 matrix. Here's what it looks like. The first column comes from where I hat landed, and the second column from where j hat landed. This gives us a beautiful general form. For any linear transformation, we can package its effect on the basis vectors into a 2x2 matrix, and this matrix completely captures how the transformation deforms space. A matrix is just a way of storing where the basis vectors land. This is why matrices have the structure they do. It encodes the transformation of space. Now that we've packaged our transformation into a matrix, how do we actually use it? Suppose you're given a vector and a matrix. How does multiplying the matrix by the vector tell you where that vector lands after the transformation? Here's the beautiful part. Matrix vector multiplication exactly mirrors what we've been doing. You scale the first column by x and the second column by y. Then add them together. This gives us the complete matrix vector multiplication. Let's see this in action. The matrix multiplication tells us exactly where each vector lands under the transformation. Matrix vector multiplication is just a weighted combination of the matrix columns, which are our transformed basis vectors. And that's the beauty of matrix vector multiplication. It's not just a computation, it's the transformation itself. Now let's step back and look at the most general case. For any 2x2 matrix, not just our specific example, the same story holds. The matrix describes where the basis vectors go. The first column tells us where I hat lands, and the second column tells us where j hat lands. Then for any vector x, y, the transformation follows a simple recipe. Multiply x by the first column, multiply y by the second column, and add the results together. That's matrix vector multiplication, and it's exactly how 2D linear transformations work. It can rotate, it spins the shape around the origin. This is a shear, it slants the shape, shifting its points horizontally or vertically while keeping areas parallel. This is a scale, it changes the size of the shape, making it larger or smaller. Every 2x2 matrix represents some transformation, and every transformation can be understood through where it sends the basis vectors. We have covered the visual rules of linearity, how to represent transformations with matrices, and a general method to solve them. Grab your curiosity, because next we are stepping into the world of linear systems. How to spot linear vs nonlinear, why additivity matters, and how matrices solve it all. Thank you for watching. Don't forget to like, share, and subscribe, and we will see you in the next episode. Stay tuned. This video is made by Astha Joshi. Keep learning, and I'll see you in the next video.